In this video, I'll be going over the sum and difference identities. So suppose we have sine of 30 degrees plus 120 degrees. It may seem obvious or intuitive to think of this as sine of 30 degrees plus sine of 120 degrees. So the question is, are these two expressions equal? Well, let's just simplify the left and right hand side to see what we end up with. On the left hand side, well, I'm going to add the two angles inside the parentheses, inside the argument. So 30 degrees plus 120 degrees is 150 degrees. Sine of 150 degrees, that's in quadrant 2. Sine is positive in quadrant 2. We're going to end up with 1/2. On the right hand side, I have sine of 30 degrees, which is positive 1/2, plus sine of 120 degrees is square root 3 over 2. So when I add these together, I get root 3 plus 1 divided by 2. So what we can see is that these expressions are not equal. So, in other words, the tendency we have when we have a sum inside the argument, or not the tendency, but maybe our first thought is to kind of like distribute the sine function through into each term of the argument. But we don't want to do that. So we don't want to say that these two things are equal. So what we need is a way to evaluate something when we have a sum inside of the argument of a trig function. So that's what this video is going to be talking about. So here are the sum and difference formulas for sine. So the only thing that's different for the sum for sine and for the difference of sine, well, if we have a plus symbol, if we have a sum in the argument, we're going to have a sum in the expanded form. And then if we have a difference in the argument, we're going to have a difference in the expanded form. So it's sine of A, cosine of B, and then plus or minus sine of B, cosine of A. So we can write this, or we can summarize this into one equation. If we have sine of A plus or minus B, we're going to take sine of the first angle times cosine of the second angle, and then we keep the sign the same. So if we're adding initially, we're going to add in the expanded form. If we subtract initially, we're going to subtract in the expanded form. Then it's going to be sine of the second angle times cosine of the first angle. So that is the sum formula for sine. And the sum and difference formulas for cosine. So for cosine, we reverse the sign. So if we're adding in the initial argument, we subtract in the extended or the expanded version. If we initially have a difference, we're going to add when we expand this out. So I can summarize this. Cosine of A plus or minus B, what we're going to have is cosine of A, so cosine of the first, times cosine of the second angle, and then we reverse the operation. So if we add initially, we subtract, or if we subtract initially, then we add. And then sine of A, sine of the first angle, times sine of the second angle. So these are the sum and difference formulas for sine and cosine. So let's see how we can use these. So this first example says to find the exact value of sine of 165 degrees. So when the question says to find the exact value, that means it doesn't want a decimal approximation. Now, we could type this into the calculator, 165 degrees, making sure we are in degree mode, and we get a decimal 0.2588190. Now, this isn't an exact value, it's an irrational number that's in a decimal approximation of an exact value. So what we're going to do is we're going to use the sum or difference formula for sine in order to get an exact value. So as a refresher, sine of A plus or minus B is sine of the first, cosine of the second. We keep the sign the same, sine of the second, cosine of the first. Okay, now what we have here is 165 degrees. We want to write this as something that is of the form a plus or minus b. And we want a and b to be values that are on the unit circle. So, for example, if we did, 130 degrees plus 35 degrees, both of those add up to 165. However, 130 and 35 are not values that we know on the unit circle, so we don't want to use those angles. So we need to pick two angles that either add, when added together, or subtracted, give us 165. Now there's multiple ways we can do this. The first one I think of is 120 degrees plus 45 degrees. If we add those together, those equal 165. We could also do 210 degrees minus 45. That also equals 165 degrees. And there are many more that we could pick. So I'm going to do 120 degrees plus 45 degrees. So sine of 120 degrees plus 45 degrees. Okay, and what I'm going to say is A is going to be 120, B is going to be 45 degrees. So when I just expand this out, I get sine of 120 degrees times cosine of the second, which is 45 degrees. I added initially inside the argument, so I'm going to add when I expand. Sine of B, which is 45 degrees, cosine of 120 degrees. Okay, at this point we just need to evaluate each of these four trig expressions. And if you don't know the unit circle, this is when life is really going to start to be pretty painful for you, because I have to evaluate four different values from the unit circle. So sine of 120 degrees, that is square root of 3 over 2. Cosine of 45 degrees is root 2 over 2, plus sine of 45, root 2 over 2. Cosine of 120 is negative 1/2. Okay, and then we just multiply these together, so I get root 6 over 4 plus negative root 2 over 4. So combining these, I get root 6 over, I should write it like this, root 6 minus root 2 all over 4. Okay, so that is sine of 165 degrees. Now, if you were to type this into the calculator, square root of 6 minus square root of 2 divided by 4, we do in fact end up with that same decimal approximation that we found previously. So this is a way that we can check our work, but we want to get an exact value, and that's what we found here. We don't want a decimal approximation. Next up, let's find the exact value of cosine of pi over 12. Now, again, pi over 12 is not a value that's on the unit circle, so what we want to do is come up with two angles that add up or subtract to pi over 12. Now, when we're dealing with an angle in radians, it's not as easy or obvious to pick the two angles we want to use that sum or subtract to pi over 12. So one strategy is to convert that angle, pi over 12, into degrees. So pi over 12, to change that into degrees, we're going to multiply by 180 over pi and get the pi to cancel. And then we can multiply 180 and 12 both by, I think 12, but let's just do 6 first. Oops. So 180 divided by 6 is 30, 12 divided by 6 is 2. So we end up with 30 over 2, which is 15 degrees. So we could just as easily think about this as cosine of 15 degrees. So two angles that add up to 15 degrees, or subtract to 15 degrees, are 45 degrees minus 30 degrees. We could use that. We could also use 60 degrees minus 45 degrees. We could use 135 minus 120. Each of these angles that I'm selecting are all on the unit circle, so any of them would work. Similarly, if we want to stay in radians, which is what we had up here, well, pi over 12, I could write that as 4 pi over 12 minus 3 pi over 12. And if I reduce these, I get pi over 3 minus pi over 4. So I could also think about cosine of pi over 3 minus pi over 4. Pi over 3 is 60 degrees, pi over 4 is 45, so these are actually exactly equivalent. So whether we stay in radians or degrees, it doesn't really matter. What matters is we come up with two angles that can subtract or add to either pi over 12 or pi over 12 or 15 degrees. All right, so cosine of, I'm going to use what we came up with in radians. Okay, so we're going to let A be pi over 3. We're going to let B be pi over 4. We don't want to use negative pi over 4 for B. So we say cosine of the first, cosine of the second. We reverse the sign. We had a difference. Now we make this a sum. Sine of the first, sine of the second. Okay, so cosine of pi over 3 times cosine of pi over 4 plus sine of pi over 3 times sine pi over 4. Multiplying these out, or rather evaluating each of these, cosine of pi over 3 is 1/2, cosine of pi over 4 is root 2 over 2, plus sine of pi over 3 is root 3 over 2, and then sine of pi over 4 is root 2 over 2. Multiplying everything together, we end up with root 2 plus root 6 divided by 4, and that is cosine of pi over 12. So these types of problems are pretty straightforward. The tricky part is finding the angles that will sum or subtract to what's given to us. Okay, in this example we want to verify this trig identity. So what we notice is that this right here is a difference. So we'll use the difference formula for cosine, letting A be x and B be 3 pi over 2. So recalling what the difference formula for cosine is, cosine of A minus B is going to be cosine of the first, cosine of the second, plus sine of the first times sine of the second. Okay, so we'll expand the left-hand side here. We're going to say cosine of the first times cosine of the second. Again, don't write negative 3 pi over 2. And then because this is a difference, we will add sine of the first, sine of the second. And then that's equal to negative sine of x. Okay, so let's evaluate each of these trig functions. Well, cosine of x, nothing to do there. Cosine at 3 pi over 2, that has a value of 0, plus sine of x, sine of 3 pi over 2 is negative 1. So 0 times cosine of x is 0. Sine of x, didn't write an x in there. Sine of x times negative 1, well that's just negative sine of x. And that is what we have on the right-hand side. So that's it. So we can use the sum and difference identities to find values like we did back here, and we can also use them to verify a trig identity. Now we've seen the cofunction identities in some other places, and here they are. And when we did this, I think when we saw this previously, we looked at a right triangle to verify these identities. But we can also do this with the difference formulas. So suppose we have cosine of pi over 2 minus theta. Well, to expand that, we're going to say cosine of the first times cosine of the second plus sine of the first times sine of the second. Okay, cosine of pi over 2 is 0 times cosine of theta plus sine of pi over 2 is 1 times sine of theta. So So this becomes 0. We're left with 1 times sine of theta, which is sine of theta. So that matches with what we got up here. So we can do something similar for the rest of these cofunction identities. And let's try and verify this trig identity. We have cosine of x plus y divided by cosine x times cosine y is equal to 1 minus tangent of x times tangent of y. So the first thing I'm going to do is expand this using the sum formula for cosine. So anytime we have an argument where it's a sum or a difference, we can think about using the sum or difference formula. So cosine of the first times cosine of the second minus sine of the first, sine of the second, divided by cosine of x times cosine of y. On the right-hand side, we're going to say 1 minus, well, I'm going to rewrite tangent of x and tangent of y in terms of sine and cosine. So tangent of x is sine x times cosine x, and then tangent y is sine y times cosine y. So on the right-hand side, I'm going to get 1 minus sine of x, sine of y, divided by cosine x, cosine y. And then I want to get a common denominator between these two terms on the right-hand side. So I'm going to rewrite 1 as cosine x, cosine y over cosine x, cosine y. So what we end up with is cosine of x, cosine of y, divided by cosine x, cosine y, minus sine x, sine y over cosine x, cosine y. So on the right-hand side, I'm going to write those two fractions together, or as a single fraction. Sine x, sine y, and what we get is the exact same thing from the left-hand side. So on the left-hand side, I don't need to keep writing. If I'm not making any changes to the left-hand side, I don't need to keep writing it. I can just write it down at the very end once the left side and the right side are the exact same. So we've got it. The last thing for us to look at is the sum or difference formula for tangent. So if we have tangent of a plus or minus b, what we do is we say tangent of the first plus or minus tangent of the second divided by 1 minus plus tangent of a times tangent of b. So what this means is if we have a plus initially, we have a plus here, and then we reverse it in the denominator. If we have a minus initially, we keep it the same, and then we reverse down here. So these problems are a little bit more complex because we end up needing to simplify a somewhat complicated fraction. So let's look at an example of one of those. So find the exact value of tangent of 17 pi over 12. Well, we can rewrite 17 pi over 12 as a sum of 8 pi over 12 plus 9 pi over 12. Now, it might not look like those are values on the unit circle, but 8 pi over 12 is 2 pi over 3. 9 pi over 12 is 3 pi over 4. Okay, so we can use those two values in the argument for tangent. All right, so tangent of 17 pi over 12 is the same as tangent of 2 pi over 3 plus 3 pi over 4. I'll let 2 pi over 3 be A, 3 pi over 4 be B. So we say tangent of the first plus, we keep the sign the same, tangent of the second, divided by 1. We change the sum to a difference, tangent of the first times tangent of the second. And then it's just an exercise in simplification. Tangent of 2 pi over 3 is equal to negative root 3, plus tangent of 3 pi over 4 is equal to negative 1, divided by 1 minus tangent of 2 pi over 3, well that's negative square root of 3, tangent of 3 pi over 4 is negative 1. So we end up with negative square root of 3 minus 1 divided by 1. I have 3 negatives getting multiplied, so this is going to be a negative 1 minus square root 3. Now, this is a perfectly legitimate answer. However, sometimes we may need to simplify, or rather rationalize the denominator. In other words, we need to remove the radical that appears in the denominator. So what we do is we multiply the top and the bottom by what's called the conjugate. And the conjugate is just a version of 1. What we do is we take the binomial in the denominator and we write it, instead of a difference, we write it as a sum. So I'm going to come up here. We're going to have, we just multiply out these two binomials, so negative square root of 3 minus square root 9 minus 1 minus square root 3. In the denominator, we're going to have 1 plus root 3 minus root 3 minus square root 9. So when we multiply by the conjugate, those middle terms always cancel. And this is always going to be a perfect square. So that's a 1 minus 3 in the denominator. In the numerator, we get negative root 3, so negative 2 square root 3. And this is square root of 9, so that's 3. So negative 3 minus 1 is negative 4. So simplifying some stuff here, I'm going to factor out a negative 2 out of the numerator. I'm left with root 3 plus 2. And then in the denominator, I also get negative 2. So once this is all cleaned up, I get square root of 3 plus 2. And that is equal to tangent of 17 pi over 12. So if you were to type this in the calculator, 17 pi over 12, we're going to get 3.73205, etc. So that's the decimal approximation of tangent of 17 pi over 12.